Today we're going to go over this last section in Unit 3, and we are going to talk all about perpendicular lines. So we have some theorems here at the beginning that prove lines are perpendicular, and then we're going to get into a little bit of solving with angles and look at a proof. So starting with our vocabulary here, what I'd like to do is just draw some diagrams and give you an opportunity to just make sure you understand what these theorems are saying. So if you look at the first three, there are no names for these theorems. So sometimes we get that where there's no name and we would just summarize this theorem if it shows up in a proof. So the very first one says, if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So let's draw two lines intersecting, forming a linear pair of congruent angles. So that means if they're a linear pair, of course, they're going to be along a line, and they're going to be adjacent. So when I draw, I'm just going to draw a ray in order to make a linear pair. If they're congruent, then what I know is, since the linear pair, or since the straight angle is 180, and the linear pair is adjacent, well, then they have to be perpendicular. They end up being 90. So let me add a little bit to this. So let's just call this line G and line H. And then I'm going to call this angle 1 and angle 2. And I'm going to just make a picture that looks like this. Make this angle congruent to this one. Now we can sit here and reason out and say, well, I know they add to 180, so therefore they both are 90, which then makes perpendicular, which is true. But if I am presented with some kind of diagram that just shows two adjacent angles along a line, and they're congruent, then the next step will become perpendicular lines. So let's add over here, if angle 1 is congruent to angle 2, comma, then G is perpendicular to H. So I potentially could have this show up in a proof if I'm trying to prove I have a set of perpendicular lines. Okay, second one. We've kind of talked about this one. If two lines are perpendicular, then they intersect to form four right angles. So if I'm going to go ahead and draw two lines that are perpendicular, I'll just call this line A and line B. And so if I'm given that they're perpendicular, I can go ahead and add that right angle. Then I can say, well, all four of those are 90 degrees. Okay, and even if I maybe, call that angle 1, angle 2, angle 3, and angle 4, then I know all four are 90. I don't have to take the time to say, well, 2 and 4 are vertical angles, therefore 2 and 4 are 90, and then I don't have to say like 1 and 2 are a linear pair, therefore if 2 is 90, the other one has to be 90. Okay, this theorem allows me to just bypass that. Okay, third one down. If two sides of two adjacent acute angles are perpendicular, then the angles are complementary. All right, so I'm going to draw two angles that are adjacent to each other, right next to each other, and they are acute, which means they're less than 90. And what it says is that the two sides of it make a 90-degree angle. So that's going to look something like this. And let's just make, I don't know, some sort of ray here. So I'll just call that A and we'll call that B. Now I know that these angles, I know that this is a perpendicular angle, I guess. It makes a right angle. And so what this theorem is saying, I'm just going to number it 1 and 2. It's basically saying that 1 and 2 are complementary because they are a part of two adjacent acute angles, and then the other sides are perpendicular. All right, and so some of these theorems overlap in other concepts that we've talked about. Okay, we do have names on these last two. We have the perpendicular transversal theorem. It says if a transversal is perpendicular to one of two parallel lines, then it has to be perpendicular to the other. So let's draw a set of parallel lines. So I'm going to draw two lines that are parallel to each other. I'll just call it, H and K. Now they're parallel, so I'm going to add the little parallel marking here. And then this is saying if you have a transversal that is perpendicular to one of them, then it has to be perpendicular to the other. So what this is saying is if I have this transversal that's perpendicular to H, well, it has to come through here and also be perpendicular to K. All right, and so it's called the perpendicular transversal theorem. And the name really says a lot about it. It is a transversal that's perpendicular to the two lines. Okay, this last one here is called lines perpendicular to a transversal theorem. So I sometimes think this name is a little confusing. I think it might be easier sometimes to just abbreviate the content of the theorem if it shows up in a proof. In a plane, if two lines are perpendicular to the same line, then they're parallel to each other. So I have a plane. Okay, let's draw a horizontal line. Let's just call that line P. So this says if you have two separate lines perpendicular to the same line. So I'm going to draw a line here perpendicular to P. Okay, we'll just call it line T. If this line is perpendicular to P and I have a second line also perpendicular to line P, I don't know, let's just call it N. This theorem says, well, if lines T and N are both perpendicular to P, well, then T has got to be parallel to N. And we can actually explain this with a converse. We can say here, if I have these two, let's say these two corresponding angles are congruent, therefore T and N have got to be parallel to each other. So it's called lines perpendicular to a transversal theorem, or sometimes I just feel like it's easier to say basically what it says. If two lines are perpendicular to the same line, they're parallel to each other. All right, well, let's move on to a couple of examples where we're just going to solve for x. So really what we're doing on 1, 2, and 3 is we're thinking about what theorem from the first page allows me to solve this, okay? Because these are going to be pretty simple for you to solve. So if I look at number 1, find the value of x. So you could do a couple things. We could say here, if I have a 90 here, I'm going to go back. I'm going to kind of scroll back and forth. If I have a 90 there, then I can say the second one right here. If two lines are perpendicular, they form 4 right angles. So if this is 90, all 4 of these around here are 90. And then these two over here are the same number and they add up to 90. Okay, so you could, if you needed to, you could write this equation, or you could think about what two angles when they add to 90 are the same. So if I just continue my equation, divide by 2, we'll end up getting 45. Okay, so it's an application of that other theorem above, and it could also go into this third one down. If two sides of adjacent acute angles are perpendicular, the angles are complementary. Therefore, it supports my 90. Okay, number 2. Number 2, we could really just use, if you have perpendicular lines, all 4 angles are 90. So I can get to 90. I could also say, well, the right angle mark here and x are a linear pair. Therefore, they add up to 180. Okay, number 3 here. This can also lead to what we talked about on example 1. If this is 90, this is also 90. So I can just add together x and 2x and set it equal to 90 and solve. So that would give me a 3x and then divide by 3. So we get x equals 30. Okay, so there's a lot of overlap here on which, I guess, theorem you could use. All right, let's do number 4, and then I'm going to stop this video and just start another one, so this one's not so long. Determine which lines, if any, must be parallel and explain your reasoning. So explanations are theorems, postulates. I'll probably refer to the earlier page, and we'll see what we have. Okay, let's see. There's no one way to start this. Let me change colors here. Okay, I'm going to focus on 90 and 90. So when I see that, what jumps out to me is that two things. These two 90s are consecutive interior, and the consecutive interior converse says that the lines must be parallel. It also applies, I could also just use the theorem, the lines perpendicular to a transversal theorem. I have two different lines perpendicular to the same line. So I see that P and Q are perpendicular to S, therefore they must be parallel. Okay, so either way is going to work. I'm going to put here that P is parallel to Q. Excuse me. I mean, I guess I could say corresponding angles converse. Except if I were using a proof, I'd have to explain what those 90s are. But I'm going to write out the theorem on the first page. So my explanation is going to be lines, and I'm going to use the perpendicular symbol, lines perpendicular to a transversal theorem. Okay. Lines perpendicular to a transversal theorem. Okay, let's look for something else. How about S, T, and U? Can we say those are parallel? Okay, I'm going to look at this 90 and this 90. I could use the exact same reason I just used. If both S and T are perpendicular to the same line Q, they're parallel to each other. So right there, I could say that S is parallel to T, and really the same reason. Lines perpendicular to a transversal theorem. Now, you might be thinking, well, can't I say corresponding angles converse? I can, but I might have to add a line or two in my proof to say that I know that those two 90s are equal. And that wouldn't be hard to do, but we could add that in there. Okay, what about U? Because it sure looks parallel. Okay, there is no information along line U. No right angles, no values. I mean, there's just no way for us to know anything about those angles. So we're really stuck with U. U cannot really be linked to S or T, even though it looks like it is in the picture. Okay, I'm going to stop this video, and like I said, we'll move on. We've got a proof, setting up an equation, and we're going to look at the last couple.